All right, here comes Paul Russ talking about soft robots. Paul,
Yeah,
floor's
thanks,
yours.
Tim. Yeah, so my entree into this world of soft robotics really started out a couple of years back when I was at the CRI in Paris and was invited to attend a session of the Interdisciplinary Research Center, the IRC at Cambridge. And the discussion was about new materials that were being used um, in the employ basically of a large part of the application was in robotics. And at that point, I was sort of focused on biotech, on synthetic biology specifically. And as the conversation continued, the discussion was all about materials that were made out of all sorts of different polymers and silicon. But I sort of began to wonder whether there wasn't any opportunity or possibility of using bio-based materials and integrating them into that environment. No one had really thought about that or given it too much thought. And so I sort of started to delve into that, and that led me into some exposure to what was going on in soft robotics. So I thought I'd take a few minutes here to sort of go through and share with you that investigation. I guess what's called a journey these days, for want of a better term, and do a couple of things. I mean, basically, the presentation is organized with two parts, Act One and Act Two. And Act One basically is where is soft robotics today, and the Act Two is where is it going. So without further ado, I'm gonna, as an indicator, this slide here, this graph shows a number of articles published. Now, this isn't a be-all, end-all indicator, but it does give some idea of how the field of soft robotics has evolved over time. And you can see in about 2008 starting, but really hitting peak in 2010, 2011, there's a step increase in the number of articles published. This shape, as anyone who's north of the Mason-Dixon, Tim, probably very familiar. Growing up in Boston, I have a sense of this. This is what we would call a hockey stick, or in Boston we would call a hockey stick. But anyway, this is really indicative of how the field has transformed over the last decade or so. And the question is why? So what is it? What's going on around 2010 that leads to this change? And I think the answer to that gives some frame to the rest of the presentation. So the answer to that is caoutchouc. I hope I'm pronouncing these right, but one is an alloy of nickel and titanium. The other is a sort of a natural rubber product. And there's a whole host of new materials that start to take shape at around this time. A whole class of materials called elastomers, which are effectively silicon-based that can be stretched to extreme, to extremes, and then can revert back to their original form. Liquid metals, all sorts of soft metals, and also at the same time, no news to anyone on the call, but AI as well is starting to become a thing and starting to hit the mainstream. And so those two things together form the bedrock of soft robotics and have really propelled it forward to where it is today. So before we go too much further, I think it makes sense to just as a level set and as a baseline, just to sort of understand what soft robotics actually encompasses. And the important thing is, I think there are two parts to this. One is what the robots are actually doing, and this whole issue of being able to achieve, as I say here, a high degree of adaptability and flexibility. And then this, on the other side, is the materials that are being used, compliant materials, pliable joints. And then the third part, which is using biological systems as the inspiration and guide for these robotic solutions. So the outline I just mentioned before, there are three themes that you'll sense and you'll see sort of weaving their way through the presentation and through the field itself. And that is high degree of complexity, uncertainty, and variation. So any solutions that are developed and any approaches that are taken have to deal with, address, and accommodate these three things, all of which are implicitly connected. So where are we today? The fundamentals, as I call them. So if we talk about, soft robotics, and here sort of from a philosophical standpoint, but I think this has ramifications and implications for how to understand some of the nuts and bolts of the solutions that are being developed. There are three key themes that I just want to touch on briefly here. Once again, with this idea of establishing this framework. One is embedded intelligence, morphological computation, and compliance. So embedded intelligence, really the term originated with Alan Turing 70, 80 years ago. And the whole concept is here, intelligence we should understand is in the context of artificial intelligence. And we usually think of artificial intelligence as being based on digital entities, on algorithms, on data processing, and so. But in the soft robotics world, it's really this combination of bodies, physical presence, and intelligence. So the sort of the fusion of the two. And there are a whole host of implications because of that. So the issue, one of the key issues is, and this is sort of what the question that EI tries to answer is, how to achieve more natural and effective robot behavior. And really the issue is how the robot interacts with the environment that it finds itself in. So we've got, on the one hand, sensors, for example, for perception, and actuators for interaction with that environment. But it's really this combination of the brain, body, and environment, that triangle, that really is at issue, and that leads to a lot of challenges in trying to create robotic systems that are functioning and that are behaving in a way that have any use or impact. And so, EI depends as much on algorithms and data processing as it does on physical forms and material properties. Now, morphological, and I should say also, and we'll see how this plays out later, but it integrates decision making and perception from intelligent algorithms with behaviors and controls from the field of robotics. So that's an important concept to keep in mind. Morphological computation refers to, morphological here referring to the body. Computation, I think, speaks for itself. But the idea that if we think about this inspiration from biological systems, the complexity and the difficulty but necessity of trying to figure out how to quantify and develop quantitative models for computation that are based on physical phenomena that are observed in nature and natural biological systems. The third one, compliance, has sort of two aspects to it. One is compliance of the robot to the environment that it's in and ability to conform to objects that it encounters. But there's another sort of sense of that, and that's referred to as a state of compliance. But there's another sense to that, and that is compliant. You'll see reference to compliant materials, which are some of these soft materials, some of these new materials that I was referencing before, that are specially adapted to the movement and behavior of soft robots and their fabrication and construction. So I missed out a block here, but basically just the basic components of any robotic system. So, and we'll get into these a little bit in the presentation that follows, but actuators, sensors, their whole interfaces, their whole host of things that make up a robotic system, but these are the basic ones. So an actuator.
Wait, hang on, Paul. What was the B? What was?
Well, those are interfaces. So there are all these interfaces that have to be developed too, and we'll see an example of this later on. Yeah, sorry about that. But yeah, that was sort of, so there are these actuators, sensors, and then mediating. There's a key role for interfaces on a variety of different levels, and we'll see some examples a little bit further on. Yeah, thanks for the question. So actuators, simply is some component, some device that enables a machine to move by converting energy, and it could be in a variety of different forms, into a mechanical force. So I should say, one of the earliest actuators that's referenced in the soft robotic realm is something called a PAM, a pneumatic activated muscle. Basically, this is a rubber sleeve that, when inflated with air, would expand axially but contract radially. And the invention of this was really the target, and the goal of this was to help people who were suffering from polio and expand or enhance their mobility or limited mobility and give them a little bit more freedom of motion. But as the field has evolved, there are all sorts of different types of actuators that have been developed. And probably the most common one, and the one I'll feature next and talk about briefly, is called the pneumatic network. And I'm never quite sure whether it should be pronounced pneunet. If I've got my French hat on, it should be pneunet. But I suppose if we think about it as pneumatic net, maybe it should be pneunet. Anyway, I leave it up to the audience to vote and decide which pronunciation would be the most appropriate. But basically, the concept is, in its essence, is quite simple. In application, could be quite complex. But basically, the actuator consists of two layers. The constraint layer that I mentioned at the bottom, that goes by a number of different names. You'll sometimes see it referred to as the inextensible layer. I've also seen it referred to as strain-resistant layer, which can be confusing for biologists who have a different idea what strain means. The top layer, unfortunately, for the top layer, so maybe an act of discrimination, is usually only just referred to as the outer layer. The important distinction between the two is their degree of flexibility and stiffness. And what basically the principle of this is that these layers contain a series of receptacles or wells and channels. And the channels, accept, or you can pass a gas or a liquid through those channels and fill the wells, and then pressurize either the gas or liquid to then deform the shape of the actuator and create, as you see on the right, this top outer layer deformation, which is essential to mobility and motion. Now, this is an abstraction, of course, and as I'm sure you can easily imagine, there can be all sorts of permutations and parameters that are involved that can be adjusted, modified, and refined. So if we think about just the materials that are used, the thickness of the layers, for example, the geometries, as they call them, of the wells, all these things have some impact on the behavior of the actuator and the degree to which it flexes or deforms. And also, these actuators can be made up of different links or segments, each of which can be actuated in a different way. So that leads to a lot of variation and variability that's required actually for allowing the robot to interact with a very complex environment that it operates in. So I talked about the pneunet or neunet, depending on how you look at it. And a very simple case, first of all, what we looked at was the simple bend configuration. But in fact, there are three classes of configuration. So we've got the bend, there's also the twist, and the extension. But by far, the bend is probably the most common and the most easy to implement. I should also mention the material that's used most commonly in that constraint layer is a silicon-based material called PDMS, and the outer layer, very often Ecoflex. And PDMS has a certain inflexibility to it, which accounts for its use in that constraint layer. Whereas Ecoflex, on the other hand, as the name suggests, is very flexible. All of these are rated on a scale that's called a Shor index. And the Shor index is a scale of numbers that based on the number that applies, then it gives you some idea of what the flexibility quotient is. So for instance, just as a way of reference, the PDMS layer designated here or featured here has a Shor value of 50. And there are a lot of different, number of different categories of in the Shor system, but basically this Shor A refers to this kind of soft material. There's also variability in the types of actuators that exists. So as the name suggests, photosensitive actuators are activated by illumination. Dielectric elastomer actuators by electricity. So typically you would have a sandwich where you have two electrodes and the actuator in between. And that flexing that we saw is determined by the amount of electricity that you pass through the voltage through those electrodes. And then finally, combustion-driven actuators, really taking advantage of the properties of gas to expand and in some cases combust in a managed way to also achieve the same thing. So I'm going to now go to the, we were talking about AI briefly in the discussion, and AI has started to take hold in the soft robotics world because it's uniquely suited to solving some of the problems and challenges that people designing soft robotic systems face. And there are two specific areas where AI is applicable. Well, there are quite a number, but the two most important, and that I'd like to talk about here, are in soft robot control and the design of components for soft robots. So if we think about control, we can look at specific machine learning algorithms and AI applications that are sort of, each one has specific applicability to one or the other of these categories. And so I'm going to talk about specifically reinforcement learning, which is very often used in the control of robotic systems, and then generative AI in the realm of design of robot components. So if we think about reinforcement learning is really adapted to decision making. So it uses a trial and error method where the model is rewarded for making correct action, taking correct action, making correct decisions with a reward, and it seeks to achieve the objective that's been set by maximizing rewards. Now, in of itself, this is quite valuable when we think about the importance of decision making to robots in an unconstrained environment. But what's lacking is this other component, which is perception, and that the robot really, just making decisions in a vacuum, which I know we've seen instances of probably in the political realm most recently, doesn't work so well in the robotic realm, and that has to be somehow combined with and paired with a perceptual aspect, an idea that the robot sort of understands or knows where it is in the world. And so deep learning suggests itself as a method of handling complex data sets and finding and determining patterns within those data complexes. And so at the moment, or where things have gotten to, there's a type of algorithm, models that have been developed based on what's referred to as deep learning reinforcement, which combines the best of both worlds, if I can call it that, the decision-making capability that reinforcement learning supports, and then deep learning for that understanding of the environment, being able to tease out important and valuable relevant patterns within a large complex of data. Now, I'm going to spend a little bit more time on generative AI, generative models, because that sort of captured my attention. But if before we get into the actual application here and discussion of what the value is, I think it's important to step back and look at the design environment in general. So as you know, it's no secret, the design environment for soft robotics is very complex because you have to take into account a number of different factors at once and figure out how to balance them in a way that leads to a viable solution. So these could be anything from structural design, material properties, control strategies. Those are just to mention just a few. And then there's this sort of laborious iterative process that's involved in the fabrication of components that are used in soft robotic systems. So this leads to an environment, a design environment, which is, and once again, thinking back to our themes, it's extremely complex, has a lot of variation and a lot of uncertainty. And the design methodologies that have been used really don't measure up and aren't able to accommodate this level of complexity and variation. So we think of models such as topographical optimization, TO, MBDO. These are all you know, design methodologies that are focused on optimization. So their strength is really refining, improving on designs in some shape or form that exist and making them better, or sort of innovating within that space. And so effective at what they do, but they're working within a limited design space that's constrained by a specific set of parameters. So there's this whole exploration element that's critical to coming up with innovative new soft robotic component designs that just isn't available, it doesn't exist in those design methodologies that have been used traditionally. So how to address that? Well, one way is, you know, manually. So using a person who is a creative designer who has some, you know, innovative ideas about how these designs could be conceived of and realized. But of course, there are constraints there, and a lot of it has to do with investment of time and money. Human creativity itself is a little bit of a malleable sort of thing, and not always on call when you need it. So generative models have emerged as a potential application for coming up with innovative designs for these different kinds of robotic components. So the value of the generative AI based models are, one, that they're based on evolutionary algorithms, and which sort of lend themselves to this kind of exploratory investigation and development. They take advantage of graph encoding, so finding links between or establishing links between objects, and they're suited to dealing with large complex data sets that have minimal labeling. Almost, I would sort of classify them as unsupervised, which once again accords with this whole, you know, real world environment that these robots are dealing with, which have a lot of randomness associated with them, and a lot of things that aren't necessarily known in advance or well established or labeled. But generative AI, as generative AI models, have their own limitations, and there are two that are quite notable. One of them is that they are quite computationally intensive, and that sometimes makes them a bit, you know, it's a bit costly to take advantage of them. The other one is there can sometimes be a fairly significant gap between the simulation space that the models are applied to in developing these solutions and the real world. So there's a sort of a lack of quality there that impedes that sort of transitioning from the simulated world, where all the design work is being done, into the real world. So the state of the art these days is, and this is gaining some traction, has garnered a lot of attention, is what's referred to as diffusion models. So this is a class of model within generative AI that has some specific advantages and applications for soft robotic design. One is that it accounts for and is able to provide some good estimation of uncertainty. So it's using, instead of working with point data, it's using with a probabilistic distribution of data to work with variables that are not necessarily well understood or defined. Once again, thinking to the environment here, this is quite applicable and valuable given what the robots are challenged with and what they have to do. Behind that, and sort of connected to it, is latency variable sampling. And I should note here that the diffusion model doesn't actually use latency variable sampling directly. And latency variable sampling is basically deducing from two known variables a variable that might not be readily apparent. And the diffusion, which is valuable, of course, in this context, and connects this whole idea of being able to come to grips with uncertain parameters, uncertain variables, but it's not very efficient. And so by taking advantage of the techniques that it does use, the diffusion model dispenses with latency variable sampling, making it much more efficient. And there might be a question, okay, so how does it do it? And I won't get into it here, but it involves, say, Markov chains, a couple of other techniques related to that. But basically, they're much more computationally modest, I would say, in comparison to what's required for latency variable sampling. And then finally, this idea of long-range dependencies, be able to find dependencies in the data that with data points that are quite distant from one another. If we think about in the natural language processing world, Euclidean distances, and this is a boon for designers who really, can take advantage of this to, design more intricate structures and design more complex functionality into the components that they're working with, because the model is so much better at being able to find them and discover them and describe them. So here is a design. So we're back to our old friend, the soft actuator, and a case of developing soft actuators using two things. One is the diffusion model that we just talked about, but also some evolution in text-to-image capability, which is now evolved to a point where it's possible to have text to 3D model. So you input text and you get, and you can create 3D models using that. So by using that capability, text to 3D modeling, and then applying the diffusion model that I was just describing, you can come up with a whole range of fairly unique purpose-built actuators that are very effective in a robotic system. Now, the way this works in practice is that there's a database, if I can call it that, of characterizations of actuators that exist, soft actuators that exists. Fairly constrained, it's about 70 samples strong, but the people who worked on this augmented that and then spent a whole lot of time curating, if I can call it that. So as you can see here in the example, coming up with fairly precise descriptive representations of those 3D models according to certain rules that they developed, and then making that a model would be trained and based on those descriptions that have been developed, connected to the 3D models that existed in the database, and then using the diffusion model to then, first of all, test the applicability of what I would call prompt engineering, prompts that are developed outside of what is curated, but then to come up with new designs and new permutations based on textual input. So I'm just going to now go to the point where soft robotics is going, and I might just make sure I'm on the time here. I guess we're sort of at the end of time.
Yeah, we started a little late, but
all right. Well, I'll try to go a little bit quickly here, but there's probably one or two things I can cut out to work it within about 5 minutes or so, if that's okay. 5-10 minutes.
Sure.
Okay. So there are, if I can call it, if we look at where things are going from here, next steps. So there are three classes of development, at least the way that I've conceived this, in new solutions, new components, and so one of them I'm calling incremental. So things like making better gripper devices, which are well known, well established, and this would be coming up with actuators that have been refined in such a way that, for example, can accommodate or make use of a hard shell combined with, on the other hand, wells that can be a series of 4 wells that can be expanded with pressurized liquid or gas, and that combination of the hard shell, which gives the force that's necessary to accommodate the variation in the wells, each one of which can be inflated independently of the other, increases the range of motion of the gripper, allowing it to adopt arbitrary postures, as they call it, and ones that might be adapted to things that are, say, off the conveyor belt or manufacturing line that require a little bit more refined manipulation. Greatly forward therapeutic applications. I do have an example of this, but maybe I'll dispense with that given the time constraints. But basically, this idea that there are three conditions that have been laid out that successful solutions here should meet or have to meet. One, that they're biodegradable. Number 2, they're sustainable. Number 3, autonomous. And there are solutions that are in development or have been developed that satisfy the first 2 conditions. But it's the autonomous part that's really a big challenge, especially when just this whole class of robots is being developed that are ingestible and that are being used, for example, to be able to make repairs, to deliver therapeutics, to survey the gastrointestinal tract. And finally, and I'll spend a little time here because that's sort of what I looked at and what sort of got me into this in the first place, is what I would call bio inside. So we've been talking in a low-level way throughout this whole thing about these robots that take their inspiration from natural biological systems, and you'll see reference to biological mimicry, biological inspiration, but this really is the next step, which is incorporating biological elements and components into a robotic system in concert with some of the elements and components that we were just talking about. And so that sort of caught my attention, this idea of what's being, in a general way, referred to as biohybrid, or I've termed bio inside. And I'd like to just sort of quickly give an example of that that I came across. So this biosensing robot that's been developed, and this is coming out of Carnegie Mellon. The goal of this was to be able to control a robot with a bio-generated signal. The implication of this and what they were trying to do by doing this, besides a proof of concept, was ultimately to be able to reduce space and improve environmental compatibility in this robotic footprint. And this biosensing robot draws on 2 developments, or 2 traditions, if I can call it that. Some success that has been had in development of cells that are cultured on PDMS, this material that we talked about before, silicon-based material. And this idea of what I'm calling micro devices or micro machines, the fact, the idea, and this is familiar to anyone who's involved in synthetic biology, the fact that you can engineer cells to do different things, to act as sensors, for example, to do computation. And so it's basically drawing on these 2 developments or trends that sort of form the base for this biosensing robot solution. So I'm just going to get into the pieces of this. The whole idea here is converting from one form of transmission or signaling to another. So going from this biochemical signaling and the sensor side of this to the actual actuation on the mechanical side using the interface. And this is really what the core and heart of this solution is this interface between bio and mechanical, or bio and electrical, as I've called it here. So I'm not going to talk about the actuator because we've already talked about that. And the actuator in this case is basically some iteration of that PNU or NUNet actuator that we talked about before. So I'm going to focus really attention on the sensor part and the interface part, which I find are the most unique and interesting to consider. So if we think about the sensor, there are a number of different parts to this and a number of different challenges that were faced in developing the solution. So in its essence, the idea is to engineer bacteria, E. coli, in such a way that they respond to a chemical in the environment by expressing a protein, effectively a fluorescent protein. So it sounds straightforward enough, but to be able to do that in practice is not so straightforward. And the issue really is, and this is this membrane that I have highlighted here, is to figure out a way to allow the isopropyl to make contact with the engineered bacteria and expose them to it without making it possible for the bacteria to escape. And so the membrane was developed in such a way that it had to strike a balance between IPTG, or this isopropyl chemical, in without letting the bacteria out. You can see here that these bacteria, as I've showed them, are in different wells. This whole well system is made out of the PDMS material that we talked about, and underneath some fluidic channel that allows for the introduction of the bacteria into each respective well. So now we're going to go to the interface part of this, or what I referred to as sort of the electrical part. But basically, you've got to figure out some way of exciting the protein so that it fluoresces and that you can observe it in some way, either through microscopy or through plate reader. And then you have to have some way of receiving it. And I'll go into the receiver part because I think that's quite interesting in a minute. But basically, the idea was to use an LED that was operating at a wavelength that would excite the bacteria, the protein, enable it to fluoresce. The photoreceptor is basically a phototransistor that is capable of receiving light, and based on the intensity of the light, adjusting the voltage that goes from a transmit leg of this to a receive leg, and measuring that voltage variation as the illumination changes. The whole thing mounted on a flexible printed circuit board, a PCB. Where things go from here, the data that's collected, that variation in voltages, it goes to a CPU. Before I get to then what happens after that, I will talk about the actuator just in passing. But basically, this whole thing, these two parts that we've just talked about, are mounted into and on a actuator, sort of the type that we just talked about. And the material has to be of a certain flexibility, or flexible but not too flexible. So once again, striking that balance so that as the actuator moves, the bacteria are not affected, and the whole structure doesn't sort of fall apart or collapse. And so there too, you have to sort of find the right way of once again thinking to that Shore system of finding the right degree of stiffness that's stiff enough to keep everything in place, but not so stiff that it can't accommodate the movement of the actuator. So what happens in practice then is that this whole system descends into a bath, and the bath is either has the IPTG introduced or not, as the case may be. And if the bacteria respond, and you can then detect the fluorescence that indicate the IPTG is present, then the robot will not act. The whole idea is to get the robot to know when to take action. And the action in this case is taking something and lifting it and putting it into this bath. But once again, if G is detected by this system, then ultimately the data from the voltage change is recorded, stored in the CPU, and the threshold set. And so the robotic arm acts according to what the level of that threshold is. And if the threshold is exceeded, it doesn't move. If it's not exceeded, then it moves and goes ahead and picks up the object and puts it and places it where it's supposed to be placed. And so, there's, of course, a couple of issues with this. So one is that, it is only adapted to responding to one type of chemical in the environment, or one stimulus, if I can call it that. The other is that, it's a certain, it's not probably speedy enough for industrial use. Scalability is also an issue. And finally, safety. So you can imagine that people might be a little bit skittish about having a robotic system like this that operates making use of bacteria. Some queasiness about the inherent safety issues that are related to that, whether they're justified or not. And then one thing perhaps that maybe was a little bit of a disappointment or letdown is that this whole pneumatic system, the actuator, is still made out of PDMS and doesn't really incorporate any, it isn't a biologically based material. And I think that that's something that's still a ways off. However, I will note once again that in that sensor part of that solution, that there is, the bacteria that we talked about, the cells are cultured on the silicone substrate. And so that does give you some sense that there is some future potential there that can be taken advantage of on a larger scale. I'm just going to close now with a general conclusion, and that is that basically where we find ourselves today in the world of soft robotics is that it's a very complex world, and one that is, of course, getting more and more complex. No question about it with some of these things that we've touched on. Luckily, there are tools, solutions, approaches, techniques that are in development or have been developed that are well suited to and adapted to such a complex environment, and can actually take advantage of the complexity to turn it to advantage and come up with new solutions. And I think the third part is that this will open up a lot of new opportunities that are today either imagined or not yet conceived. And we can think about the biosensing robot that I just talked about. There are a couple of other medical solutions that I didn't mention that also point to new opportunities on the horizon that can be realized with some of these tools that have been developed. So since we're out of time, I guess, or come to the end of time, I'll close here. But anyway, hopefully that was at least somewhat coherent, insightful, and give some food for thought.
Yeah, that was great, Paul. I've seen some thumbs up. There we go. I'll stop it.